Good afternoon, all and one present over here. We would like to introduce our next resource person, Dr. Sandip Paul, Department of Computer Application, Dr. B.C. Roy, Academy of Professional Courses. Dr. Sandip Paul has been serving as an associate professor at Dr. B.C. Roy, Academy of Professional Courses, Durgapur since 2016. He earned a PhD in Applied Mathematics from the University of Calcutta in 2019. With a strong academic background, including an MSc in Mathematics and Computing from the Indian Institute of Technology, Dhanbad, India, and a BSc in Mathematics from Bankura Christian College under Bardhaman University, he has made significant contribution to the field. Dr. Paul possesses 15 years of research and teaching experience. He seamlessly combines teaching and research, making valuable contribution to the academic community. Dr. Paul has authored more than 20 publications in various SCI and Scopus Index journals and conferences. His expertise span areas such as quantum mechanics, fluid dynamics, theoretical oceanography, water waves, integral equation, and statistical inferences. In this session, we shall learn about Mathematical Foundation 1, Probability and Statistics. We now hand over the session to Dr. Sandip Paul. Please, sir.
Thank you, Ria, for this nice introduction. So I'm sharing my file. Background background safe. Okay, is it visible?
Yes, sir.
Okay, so I'm going to discuss the topics in mathematics required for data science. And as we are dealing with data, we always need some mathematical tools and concepts to analyze them. And the main three pillars of mathematics which we need to learn about data is probability, statistics, and linear algebra, and the optimization techniques. We have three sessions in this FDP, and today I am going to start the first pillar. It is the mathematical foundation in probability and statistics. So topics will be covered in this session are probability theory, where we learn the different type of probability definitions, then the concept of random variables and their probability distributions, and we'll learn some special distributions like binomial, Poisson, normal, and other distributions. We'll also discuss some multi-dimensional random variables, central limit theorem, and mathematical expectations. In module 2, there are two topics. We'll learn bivariate data, and using correlation and regression concepts, we'll understand what is how to analyze the bivariate data. And the third module is the sampling theory, where we'll learn how to use the data obtained from a large set of individuals to test something or some characteristic of the entire population or a large thing. Okay, so let us start from probability theory. So whenever we want to know about the probability theory, first of all, we have to know why we learn probability. So there are two types of processes. First process is deterministic. Deterministic means where we know so the data, the information for future perfectly or with 100% confidence. For example, suppose we want to record or we want to determine the time or time spent for learning for coming 1 year. So one student can determine about the time he will spend for learning. But when if we want to know the marks obtained by the student at the end of the year, that means the marks out of 100 he will get or he or she will get is unknown. But we can understand, we can actually predict the marks obtained by the student. It can be from 0 to 100. Any marks in between 0 to 100, it can be he or she can get. So that at that point the concept of probability will arise. So we know the possible outcomes, we know the possible results, but we cannot say perfectly with 100% confidence. We cannot say what is the marks obtained by the student. So now, what is the meaning of probability? Probability is, its literal meaning is chance. Chance means the mathematical mathematical measure to describe a phenomena or happening or non-happening of some phenomena. So in probability theory, we'll learn the chance of occurrence of certain unpredictable or random phenomena. That means here we learn, suppose we are considering an experiment. Suppose we are tossing a coin. So this is the experiment which can be performed multiple times. But in a particular performance of that experiment, in a particular toss, we cannot say what will be the result obtained after tossing. So that means we are tossing a same coin in the same conditions, but we cannot say the result. But we can guess the possible result. It can be head or tail. So here the concept of random experiment comes in the picture. So now if we consider the random experiment, so we always try to know what are the possible outcomes. So if we toss a single coin, there are two possibilities, either head or tail. So these two outcomes are called the sample points or the possible outcomes. But if we consider the set of all these outcomes, it will be the sample space. Similarly, if we consider tossing of two coins, there are four different possibilities. Both maybe the head, first is head, another is tail, or first is tail, second is head, or both are tail. So in this sample space, if we toss two coins, in the experiment of tossing two coins, there are four possible outcomes. So the sample space is given here: head, tail, tail, head, and tail, tail. That means there are four different sample points. Now there are two type of sample spaces. Here in this example, you can see four possible outcomes can be defined clearly, and they are called the discrete type sample spaces. But suppose we are guessing, suppose the random that means outcomes are not can be defined are not defined clearly. It is given in some range. So suppose the arriving time of a bus in some bus stand, so it can be within 10 or 15 minutes. It can arise at any particular time in between that 15 minutes. So in that case, we'll say they are uncountable, or we can say they are continuous sample spaces. So in the next, we have to know the events. Event means any subset of the sample space. Like suppose we are tossing two coins. So if we want to know how many cases are there where the first is head. So if we see the sample space of tossing two coins, you can see only two outcomes favorable to that particular requirement. First is head, can be this HH and HT. So out of these four possible outcomes, only two will satisfy the requirement of first is head. So this is a subset of the entire set S, and this is called an event. So we can define different type of events from the same sample space. And if there be no possible outcome, suppose we are tossing two coins and one wants to know how many times we are getting three heads. So there is no outcome related to that requirement. So in that case, the number of outcome will be 0, and that event is defined as the null or impossible event. So it cannot be happened if we toss two coins. So it is not possible to get three heads, three tail, or three outcomes. And there is another type of event which will always happen. It is called the certain event. So if anyone wants to know, if we toss two coins, so how many times we get two head or tail? So we may have head or tail, either head or tail. So it will always happen. So S is the sample space. It is also the subset of S, and it will always happen if we perform the experiment. So these are the different type of events. So if we consider single outcome in a set in the event, it is called the elementary event. Now, whenever we consider different type of events, we always want to know, are they related? That means if A and B are the events, can you say they are disjoint or not? So if they are disjoint, if they have no common outcome, then we'll say they are disjoint. For example, if we consider the tossing of two coins, so you can see in the first, exactly one head or tail can be defined by the, so here I have done a mistake. These two sets can be named differently, A and B. So suppose this is the set A, first set is HT and TH, and the second is both results are same, so HH and TT. So we can see these two events have no common outcome. That means they are disjoint. Now next is we have to know we have to know the definition of probability, how to measure the probability. So if we toss a coin, if I ask you what is the probability of getting a head, we always say it will be 1 by 2. So why the numbers 1 and 2 are coming? So here the concept of classical definition coming to the picture. First, we'll try to know how many possible outcomes are there in the sample space. So as we are tossing two coins or single coin, if we toss single coin, the possible outcomes are H and T, and that means there are two possible outcomes. And as we are finding the probability of a head, so it is 1. So P of A, probability of head, will be in number of cases or number of times we are getting head, so it is 1, and the denominator will be 2. That's why we are getting 1 by 2. In the other example, if we consider tossing two coins, and if we want to know probability of both are head, that means out of 4 outcomes there will be only one outcome which is favorable to that case of getting two heads. That means in that case n of A is 1 and n of A is 4. So probability of that event will be 1 by 4. Now there is another definition, axiomatic definition. So where probability can be defined through some axioms. First of all, the first axiom is the probability of the event A from the sample space S is always non-negative. That means probability always greater than equal to 0 for any event. It will happen always. And probability of the sample space or the certain event is always 1. So that means, as we know, from the classical definition, n of S is the maximum number or maximum number of times the result can be obtained. So n of A cannot exceed n of S. So obviously the P of S is the highest probability for any event from a sample space. So it is 1. So that means from here we can conclude P of A cannot exceed the value 1. Now third axiom is, if we have a set of events, suppose there are infinite events A1, A2, so if they are disjoint, that means if they have no common outcomes, then probability of their union, that means P of A1 union A2 union up to AN or up to infinity, is equal to the sum of their individual probabilities, P of A1 and P of A2 up to P of infinity, P of A infinity. So these three axioms can define the probability differently. Now next, from the theorems or from the definition, we can write the probability of any event lies in between 0 and 1. So probability cannot exceed 1 or cannot be less than 0. Next is the for any event, for A1 to AN, for any event, any number of events. So probability of union of AI. So probability of occurrence either A1 or A2 or AN. So can be written like probability of individual events AIs and minus summation over probability of is intersection of events if we take two at a time, then alternatively plus and minus n, and ultimately probability of their simultaneous occurrence of all events. So from this theorem, from this result, we can write something. So if suppose the events are disjoint, if they are mutually exclusive, in that case, the second term, third term, and up to the last term, all are zero. All are zero, that they have no common outcome. That means their probability of their intersection is always zero. So there will be only one term, the first term, and it is the probability of individual occurrence of the event. So probability of union AI can be written in that case as summation of their individual probabilities. So from this we can say probability of A complement. That means not probability of the non-happening of the event A. So if we toss a coin, probability of happening, probability of getting head is A, then probability of non-happening of getting a tail. So similarly, we can obtain the probability of its complement. So if there are only two possible outcomes, first is the happening of A and the second is non-happening of A. So probability of non-happening of A can be obtained from probability of A by using the formula 1 minus P of A. That means here A and A complement are disjoint and they can define the entire sample space. That means they are exhaustive event. That means there is no other events in the picture. Now conditional probability. So conditional probability, suppose there are two events, one happening after another. So the probability of happening A when B has occurred earlier can be obtained using the formula. So it can be understood through the example here. So suppose we have two buckets. First bucket contains 5 red balls and 8 green balls, and we are transferring a ball from the first bucket to the second. So if we transfer a ball from the first bucket to the second, which has already 6 red balls and 6 green balls, and if we transfer a red ball from the first to second, then the number of red will be increased by 1 and the number of red ball in that case will be 7 and the green ball is 6. That means total is 13 balls are there in the second bucket. Now if I draw a ball from the second bucket and if we want to know the probability of a green ball from the second bucket if the event B or event occurred earlier, then it will be 6 by 13 because there is no change. There is no change of green balls, so it is 6, but the total number of balls from the second bucket is 13, so it will be 6 by 13. But in the second case, if we transfer a green ball from the first to second, what is happening? If we transfer the green ball, so the number of green ball will be increased by 1 in the second bucket, and if we consider a green ball from the second bucket and if we want to know its probability, we can see the number of red ball is still 6, but the number of green ball is increased by 1, it is 7. So the probability of happening or probability of getting A when B2, that means the transformation of green ball occurred earlier, so probability of green ball in that case will be 7 by 13 because the number of green ball is 7 now. So from this concept, we can define the probability of happening the event A when B occurred earlier can be written as probability of simultaneous occurrence of A and B divided by probability of B. So A dot B denotes the simultaneous occurrence. They occurred simultaneously. They occurred at the same time by P of B. But the condition is the denominator cannot be 0 if it be a null event. B cannot be a null event. If it is null, the denominator will be 0. So for any non-null event, we can apply this formula. Now we have to remember from this definition, we can get the probability of happening or probability of getting A, B simultaneously can be written like P of B into P of A given B, or in other way we can write P of A into P of B given A. Both are true, but the condition is the P of A and P of B cannot be 0. Now, if we have n events, in that case, probability of simultaneous occurrence of AI or all A in AI values is equals to probability of the first into probability of the A2 given A1 into probability of A3 given A1 intersection A2. That means in the third term you can see probability of A3 is given is obtained, but where A1 and A2 has occurred earlier simultaneously. So from here we can see probability of simultaneous occurrence is greater than 0, otherwise it is not actually satisfied. Now we'll learn the independence of events. So as we have defined P of A given B as simultaneous occurrence of P of A and B by P of B, but suppose A and B are not dependent. That means whatever result from the event B occurred does not affect the event A. So in that case they are independent. So that means from this we can say probability of A given B is same as probability of individual occurrence of A. So B is not as bring any effect on the event A. So in that case they are independent. But mathematically we can write the probability of simultaneous occurrence as probability of A into probability of B. Now, so we know the concept of disjoint event or the mutually exclusive events where the simultaneous occurrence is 0, probability of the simultaneous occurrence is 0, or P of A intersection B is 0, and probability of independent events satisfy this relation. So we always try to know if two events are independent, whether they are exclusive or not. So we have to remember things. Two independent events cannot be mutually exclusive. Okay, because if they are independent, if P of A and P of B are non-null events, then the probability of their simultaneous occurrence cannot be 0. In other way we can say if they are mutually exclusive, they cannot be independent in general. Now we'll learn how to convert the, so till now we have learned the probability in terms of events. But suppose we are defining a number related to the particular event. So in that case, we have to know the concept of random variables. First of all, we define what random variable. So suppose we are tossing 2 coins, or we are tossing a coin twice. So in both the cases the sample space is same. So we may have this type of sample space HH, HT, TH, TT. 4 possible outcomes are there. And suppose we are defining a real number related to denoting the number of heads in a particular outcome. So if we consider HH, there are 2 possible, there are 2 heads, so that's why we are putting 2 here, the number is 2. So if the result is HT, the number of head is 1. If the result is TH, the number of head is also 1. If both are tail, then number of head is 0. So here we are defining a random variable x which can take value 2, 1 or 0. So these set of values are called the spectrum of the random variable. So you can say these are the real numbers. This is the spectrum of the random variable x. So if we define the random variable perfectly, so random variable is a function over the sample space S to a real number. So you can see here we have the sample space, and we are defining a number x. So we can say this is the variable which will transfer or which will convert the outcomes to a real number by some rule, and in that case the domain is the sample space and range will be a real number. So in that case we'll write x of omega is equal to s particular value x. So in this example, omega is the outcomes of sample space HH or HT, TH or TT, but the values of small x are the results or the numbers for x. So 2, 1 and 0. So we can say the values of x in this example are 0, 1 and 2. Now, so this set of values are called the spectrum. And from the same sample space, we can define different random variables. So here we have defined the number of heads. So if I want to consider x as the number of two heads, so there will be only two values. So number of two heads are often only ones, and for remaining three outcomes, the number of head is 0. Number of two head is 0. So there are only two possible values of x. The spectrum is 0 and 1, so and so on. So we can define different type of random variable from the same sample space. Now, as we are considering the random variables, it can be of two types. First is discrete type or random variables, where we can count the variables or count the number of variables, like tossing of coin. The number of tossing of 2 coins, number of outcomes are 4, but the random variable has 3 values, 0, 1 and 2, so we can count them. But in some other cases, we cannot count the number of values of x. It cannot be countable, and we'll say they are continuous. For example, if we want to know the arriving time of a bus in some certain time period, so it can be anything. Or if we want to know the height of a student, so it can be any value in between two values. So in that case, the random variable will be continuous. So there are two types of random variables: discrete and continuous. First is countable and the second is uncountable. Now, whenever you consider a discrete random variable, it can be characterized through a function, and it is called the probability mass function. It says the probability of certain value of the random variable x, p of x, can be defined as probability of the random variable at xi is equal to pi. So probability at that value, and other than that value, the probability is 0. So, and the entire set of xi and pi, so if we consider them as an order pair, xi values and corresponding pi value, it is called the probability distribution of x. So xi and pi will define the entire distribution. So we will say all the values are given, all x values are given, and corresponding probabilities are given, and entire table define the distribution. And if we have any function, so here we can see the probability over the sample space from minus infinity to infinity to 0, 1 is the PMF. That means the probability will lie in between 0 and 1, and probability of x at any value is always greater than or equal to 0. So you always know, and probability of x equal to probability of x or sum of all probabilities will be 1. So if we add all these probability at different x values, we will get 1. Now in case of discrete distribution, there is another function we have to know, the cumulative distribution function, or simply the distribution function. So it will be the probability from the leftmost value to a certain value of x. So that means we have to add all such probabilities to get that function. So f of x is the sum of all probabilities, can be written like p of x less than or equal to small x. So it is the cumulative distribution function of the random variable x. So if we want to find the probability distribution function at infinity, minus infinity, so that means we are finding, or we are summing the probability from leftmost point to that point itself. Obviously it is 0, but if we consider the entire set of values of x, so that means f of infinity, it will be 1. So probability f of x has the lowest value 0 and f of x has highest value as 1. So the cumulative distribution function always lies in between 0 and 1. Now if we want to get the probability in between certain values of a and b are not infinity exactly, so we can get it by using the formula f of b minus f of a. So it will be clear if we consider some examples. So if we consider the rolling of two dice, and we are denoting the random variable capital X as the sum of the faces in upturned faces. So we can get the numbers 2, 3, 4 up to 12. If we toss two, if we roll two dice. Now getting two can be obtained only once out of 36 outcomes, so its probability will be 1 by 36. Similarly, 3 can be obtained twice, so in that case its probability will be 36. So you can see the numerators denotes the frequencies.
Even if the event separate from the ಅದರೊಳಗಡೆ ಬರೋಣ ಕಾಂಟ್ಯಾಕ್ಟ್ ಅಲ್ಲೇ ಮಾಡ್ತೀವಿ.
Some noise is coming.
ಮಾಡಿದೀವಲ್ಲ ಅದಕ್ಕೆ ಅಲ್ಲಿ ಅಪ್ಡೇಟ್ ಆಗಿದೆ.
So now if we have this distribution function, so here you can see the probability distribution is given, x values and their probabilities. So if we draw them, we can see the probability at the value x equal to 2, so is 1 by 36. So first bar for the first line denotes, or first this is the height denoting the probability. At 3, probability is 2 by 36. Similarly, at 4 it is 3 by 30. So in this way we can draw all the PMF or all the probabilities in a single picture, and it is the PMF of the random variable. So I have drawn this diagram using R programming, so you can use R programming to get such type of graphs. Now if we draw the cumulative distribution functions, so you can see at the point 2, so it is the first point, so at the left of this point the probability is always 0. So other than 2, the left of 2, the probability is 0. That's why this graph showing, the second graph showing, it is 0. But at 2 it is 1 by 36. Now at 3 it will be increased, and then it will be 1 plus 2 by 30, 1 by 36 plus 2 by 36, and so on. And finally, if we add all the probabilities at different points, it is equals to 1. Now, continuous random variable. So in case of continuous random variable, we cannot write the values, all values of x like previously. Here x are given in some limits or in some interval. So probability density function, actually they are the probabilities at so you can see in case of distribution mass function, we can define the probability at that point. But in case of continuous random variable, we cannot write the probability at the given value of x. So we have to define the probability in some range, or in some very close interval of x. So in between x and x plus dx, so we are considering it can be shown in the green region in the second graph. So here the probability in between x and its very close point x plus dx can be written as the probability at x, or the f of x, into the length dx. So it is the probability density function. F of x is the probability density function, can be defined like this: limiting value of the probability in between x and x plus del x.
Yes, sir. Yes, yes, sir.
Some noise are coming.
Yes, sir. Number of standard. Last year. Yeah. like what what are you saying? Your diagram one is like 20 diagram. ನೋಡಲ್ಲ ಇವರು ಸೆಟ್ ಕೊಡ್ತಾರೆ ಸುದ್ದಿ ಮೇಡಮ್ ಸೆಟ್ ಕೊಡ್ತಾರೆ ಮತ್ತೆ ಮೂರ್ತಿ ಸರ್ 22 ಮತ್ತೆ
Okay, am I audible? Okay, so we are discussing the continuous random variable. So as we are considering continuous random variable, it can be in between in some limit. So we always define the probability density function by writing the limiting value of the ratio of probability and the length del x. So if we consider a very small length of del x, so that means limiting it if it be tends to 0, in that case, so it must be delta x tends to 0. So in that case, it will be the probability density function. And in similar with the probability mass function, all fx values are non-negative, and that means greater than equal to 0. And if we consider the entire area under the curve, that means if you take the integration from minus infinity to infinity f of x dx, it will be 1. So this denotes the entire area under this curve. This curve is called the density curve, and this area, the region under the curve, is called the denotes the density or the distribution function. Now, from the given distribution, we can calculate different measures. Different measures, that means we can calculate mean, median, mode, or deviations like mean deviations, standard deviations. I have written only few of them. So first, the mean of any random variable x can be obtained using the formula. So for the discrete random variables, we will use the summation notation. So, and it is the summation of the products of x and its probability, x into the probability. But in case of continuous, we have to take the integration over the all given values of x of the product x and f of x. So it is the mean of the random variables. Now, mean deviation, it can be obtained the deviation from the mean of the random variable. So it can be denoted by absolute value x minus x bar into its probability. So if we consider the sum of these products, it will be the mean deviation. And if we consider the integration, if we consider the continuous random variable, we have to take the integration of the difference between the random variable and its mean into the function f of x. Similarly, the movements can be obtained. The rth order movements can be obtained. Rth order movements mean the area, that means the value of the or the sum of the products of the rth power of the difference into the probability. So from that, by finding the movements, we can get the standard deviation, variance like this. And the second movement, mu2, is denoted by sigma square. It is called the variance. So if we find the mu2 from the formula, we will get the variance, and sigma itself is called the standard deviation. So we need all these measures later. Now, different type of measures or different type of analysis can be done by finding the mean, median, and mode. But if we consider the non-density curve or the distribution curve, we can do something. We can get some. We will get some idea about the distribution. For example, if we have this standard normal distribution, it is a continuous curve. Which can be seen symmetric about the line z equal to 0. So you can see it is symmetric. So that means it has no its actually skewness is 0. But if we consider the next curve, it is the curve for chi-square distribution. It is a PDF of chi-square distribution. So you can see that it is skewed curve. It is not symmetric about any line. So in that case, we say it is a skewed curve. And it can be measured through Karl Pearson coefficient of skewness. The definition is mean minus mode by sigma, or we can use 3 into mean minus median by sigma. Sigma denotes the standard deviation. So we can use this formula to get the skewness or to understand the skewness of the curve. Next thing is we have to know the flatness or the convexity of the frequency curve. So what type of curve it is. So you can see here in this diagram we have 3 different normal curves. All are symmetric about the line x equal to 0 or z equal to 0. So but they are different. So the difference is they are actually convex. The difference in convexity. So it is measured by the term like kurtosis. Kurtosis can be measured by finding the ratio of mu4 and mu2 square. That means if we find the moments mu4 and mu2, and if we consider the this ratio, this will be a measure of kurtosis, or we can define the kurtosis by another parameter or another variable. It is the gamma 2 equal to beta 2 minus theta minus 3. So now in this curve you can see actually the purple color curve is more peaked than the green color. So that's why this curve is called leptokurtic. The middlemost is the red color curve is called mesokurtic or simply normal curve. If you draw a normal curve, it will be a mesokurtic curve. But in the third graph, in the green color, it is the platykurtic curve. That means its kurtosis is small, or it is less than 3. So here the red color, here the kurtosis is 0. If you calculate the coefficients, so you will get gamma 2 equal to 0 for the middlemost curve, for the mesokurtic curve. But in case of leptokurtic curve, it will be greater than 0, and for platykurtic curve, it will be less than 0. Now we'll define a few special type of distributions. First is the binomial distribution. So binomial distributions, as into the picture, if we do some experiment like tossing a coin finite number of times, or now if we calculate the number of misprint in a page, or if we calculate the marks obtained by certain number of students. So in all these cases, the total number of outcome you can see, the possible values of x is finite and it can be countable. So that means first is discrete, it is a discrete random variable, and the number of values is countable. That means we will get the maximum value of x. So in that case we can apply binomial distribution. So the requirement for binomial distribution for any random variable is n is finite. N denotes the number of trials, how many times you are performing the experiments. So if it is finite, next is if p is constant. So if you toss a coin, so probability of getting a head. So if head denotes the random variable, number of head denotes the random variable. So if we move trial to trial, there will be no change in the probability of getting it. So it is constant. So it is required. It is a basic requirement. And trials are independent. Trials are independent means the results of any experiment does not affect the results of any performance does not affect the result the next performance. So it will be the trials are independent. For example, so if we consider drawing a ball from a bucket without replacement. So if we want to, suppose there are 10 balls. For this example, I am using the first bucket. You can see if we draw a ball from the first bracket, so ignore the colors, just consider the number of balls. So if we consider a ball from the first bucket and if we want to know the probability, we can get it. So there are 8 plus 5, 13 balls. So if we draw a ball, so probability of a ball is 1 by 13. But if we consider, if we do not actually, if we draw the ball and we will not replace it in the previous place, that means in the second trial, second draw, the total number of ball will be decreased by 1. So it will affect the next trial. So, and such type of such type of experiment cannot be considered through binomial distributions. So here we have to remember these things. The trials are independent. That means happening of a certain certain part of performance, whatever we are getting does not affect the next. So it is a discrete random variable. And if we consider, if we find the probability at such values of x, it will be it can be defined in this way. So probability of x is ncx to the power x q to the power n minus a. Q p is the probability of getting x in a trial, and q denotes probability of not getting that result in a particular trial. So q is equal to 1 minus p. So in a single trial, there are only two possible outcomes, either getting a certain thing or non-getting a thing. Getting the thing is generally denoted by success, and non-getting is denoted as the failure. So there are only two possible outcomes in that experiment, either success or failure. Now, if we check their probability mass function, so first diagram is the mass function. So we can see the highest probability is obtained at x equal to 10. Okay, so if we consider the distribution like this, so suppose there are 20 possible outcomes, 0 to 20. So n value is 20. So probability will be highest at the middlemost value. So it is here x denotes the number of success. Actually x denotes the number, how many times we are getting the hit. So it will be the number of times we are getting success. So the highest probability will be at the middlemost value of x. So at the center of the value. Now if we check the distribution function of that mass function, so you can see at the leftmost value when it is 0, the leftmost value, it is the probability is 0. But as the values of x increasing, the distribution for the function is also increasing. That means the summation values is also increasing, and finally when x is 20, the total probability is 1. So the highest value is 1. So always this curve lies in between 0 and 1. Now next we will consider a continuous random variable. A continuous random variable, that means here we cannot count the number of values of x, so it cannot be countable. So so I have done a mistake here. You can see tossing a coin finite number of times is not possible here. So I have done a mistake. Forget this example. I'm giving you one more thing. Suppose I want to count the number of mistakes in a book which has infinite number of words. So the number of results or number of misprints can be 0, 1, 2 or up to infinity. Okay, so in that case it is a continuous random variable. But if I want to know the variable lies in between A and B, so suppose variable, so arriving time of a bus, so it can be in between 0 to 15 minutes. So if there be 15 minutes gap in between the arrival time of two consecutive buses, So it can be maximum 15 minutes. So it can be 0 minute to 15 minutes. A bus can arrive at a certain stand. So in that case, it will follow the uniform distribution. So uniform distribution can be defined through the probability density function, and it is 1 by b minus a. So if we draw that function, you will get when it is less than 0, the probability is 0. When it is in between 0 and 30, the probability is constant at all the points. It is 1 by b minus a, or in this example 1 by so here a is 0, b is 30, so it is 1 by 30 all the times. That's why 0.3 is all the time in between 0 and 30, and after that value the probability is 0 again. So it is the uniform or rectangular distribution. And if we draw the density function here, so if we draw the density function, obviously we have to calculate the integration value from leftmost value, that means minus infinity to certain value of x, and its function will be x minus a by b minus a. So when x is less than a, there is no value of p, or we cannot say f of x is 0 always. So if we find the integration up to 0, it is always 0. So that's why this will be capital F of x. So capital F of x is always 0, so that's why it is 0 from minus 20, or in the leftmost value of the distribution to 0, and from 0 to 30 it will follow this function x minus a by b minus a. That's why it is this learning line, and at 30 and onwards it is always 1. The probability is always 1, so f of x is always 1. Now the most important and most required distribution in data science is the normal distribution. Normal distribution says, so if we consider in the binomial distribution we have seen, if the number of trial be finite. So I am moving to that distribution once again. So you can see here in the leftmost graph, the trial, so we have performed the experiment only 20 times. Instead of 20 times, if we draw or if we do that performance infinite number of times, 1 lakh times, 2 or 1 crore times, or more than this, so in that case we'll get very close, or we'll get the lines very close to another one. So the lines are very close. So in that case, if we increase the value of n, so we'll get that random variable will follow the normal distribution. So if we increase the value of n up to infinity, it will that in that case the random variable will follow the normal distribution. So for example, if we toss a coin infinite number of times, it will follow normal distribution. Or if we consider the height of a person from entire world, so it will follow the normal distribution. In fact, for any distribution, if we consider them infinite number of times, if n be infinite, or if we consider a very large set of data, they will follow normal distribution. So that's why it is important the most. Next, it's PDF. PDF is generally denoted by x, as x will follow. So this denotes that will follow normal mu sigma square. These two are the parameters. Mu and sigma are the parameters, and if we write the function of that PDF, it will be this value 1 by 2 root 2 pi sigma into e to the power minus half into x minus mu by sigma whole square. So you can see x range from minus infinity to infinity, and sigma is always positive. Okay, you have to remember these two things. Now here in this graph you can see normal, though we have already discussed the normal graph earlier. So you can see that it is symmetric graph, about symmetric about a line. Here in this example we have taken mean equals to minus 2, that means it is symmetric, minus 2.3. so that means the graph is symmetric about the line minus 2.3, and its standard deviation is 1.2. that means standard deviation actually measures the amount of spread, how the graph is spread over the range minus infinity to infinity. So if we increase the value of standard deviation, graph will be spread over the x values or the minus infinity to infinity range. Now if we get the calculate the normal distribution, the density function, the distribution function of normal distribution, it will looks like this. So you can see this, there is a similarity between the normal distribution function and the binomial distribution function. They look similar. It is binomial and it is normal. You can see there are small line segments that are in between two consecutive values of x in binomial distribution, and if we increase the number of values of x, so the line segments will be very small, so it will looks like a continuous curve like this. So the binomial distribution will convert to the normal distribution if we take very large value of n. And one more thing we required, probability is not a probability at a certain point is very not very small. Now next is the properties of the normal curve. So there are certain properties of normal curve. Normal curve is always looks like a bell-shaped density function, and the probability of probability in between two x values a and b is denoted or can be calculated through the formula integration a to b f of x dx. But what does it mean? So if we draw the normal curves, here you can see three different diagrams given. In the first diagram, we have drawn or we have shown that the probabilities between -1 and 1. Okay, so here the normal distribution is shown, and the probability has calculated between -1 and 1, and you can see it will cover the 68.26% of the entire area. So we have seen the entire area can be considered as 100% and 68% in between -1 and 1. Okay, so or in other words, if we say the probability under the curve is 1 and the probability in between these two values is 0.6826. So we can say in this way. So if we have a normal distribution with mean mu and standard deviation sigma, so 68.26% area will be covered. 68.26% area will be covered within mu plus minus sigma. That means mu minus sigma to mu plus sigma, it will be the 68% area. Now if we consider the second diagram, so if here we have drawn the curve in between, so actually we have drawn the standard normal graph. Here we have found the probability in between -2 and 2, and if we consider the entire area be 100%, it will take 95.44% from -2 to 2. And similarly, if we consider the area from -3 to 3, it is almost 99.73% under this graph, and outside this graph it is very small. So generally we draw the standard normal curve from -4 to 4. After that we will ignore, because it is very small value. It will not affect significantly the results. Now standard normal distribution, though we have used the normal curve, so it has some specific form of because here we have considered a normal distribution with mean as 0 and the standard deviation sigma equal to 1. So if it has a specific form, specific type of normal distribution with mean 0 and standard deviation 1. And so if we write the corresponding the density function, it will be small phi of x, and it is the it is given as 1 by root 2 pi, because there was a sigma, it is 1 in this case. So root 2 pi into 1 e to the power z square by 2. Z denotes the value x minus mu by sigma. So it is the density curve of the standard normal variant. Now if we draw that graph, we can see this graph is symmetric, it is bell shaped, and it is symmetric about the line z equal to 0, about this line z equal to 0. So that means it is symmetric on both sides of z equal to 0. Now if you draw the its distribution curve, so it will be there is no option to write phi notation. It will be capital phi of x. Actually the distribution function of standard normal distribution denoted by capital phi. function. So capital phi denotes the distribution curve and it will look like this. You can see it is similar to the normal curve, but here the middlemost value is 0. Now next distribution we will consider the chi-square distribution. So chi-square distribution actually, if we consider the square of the standard normal variant. So if x be the normal variant, so then J convert to the standard normal variant by considering the transformation x minus mu by sigma. Now if we consider the square of this variant, it will be a chi-square variant. So if we consider the z square value, it will be the chi-square distribution or chi-square variant with 1 degree of freedom. So z square is a chi-square variant with 1 degree of freedom. And if we consider n such type of chi-square variant, that means n number of sum of n number of z square, it will be another chi-square variant, but the degree of freedom will be increased by to n. So here in the next we have considered xi as n independent normal variant. So if we consider x as n independent x1 up to xn, and if we consider the sum of the squares of the variables xi minus mu I by sigma I square, then it will be chi-square variant with n degree of freedom. Here n denotes the degree of freedom. Now if we draw the density function of this chi-square, it is obviously, as we are considering normal variant, and as we are drawing the chi-square variant from normal variant, so it is also a continuous random variable, and if we draw the curve, it will look like this. It is a skewed curve, and you can see it is a positively skewed, and its density function is given by this function. So in to analyze the data through some software, the function is not required actually. So there is some built-in program in different software, so it is not required all the cases all the time. We need the concepts only. Now here we have given a table of different type of distributions. There are several other distributions. I have considered only few of them. First is binomial. Binomial, if we consider the binomial distribution and if we consider the mean and standard deviation, so it is obviously the mean is NP and standard deviation is root over NP cube or root over NP into 1 minus P. As you know, Q is 1 minus P. Similarly, if we consider the mean for Poisson distribution, uniform distribution, normal distribution, they can be obtained using the formula defined earlier. So you can use that formula to get the mean, standard deviation, or even other movements of that distribution by using the formula. I'm not discussing anything about the calculation procedure. You have to note down these results only. Now, till now we have discussed a single variable defined over some sample space, but it may possible that from a single sample space we can define two or more random variables. For example, suppose we have a set of students, so we can define the height of a student and the marks obtained by that student. So first result or first information denotes a variable, suppose that is x, and the marks is denotes another variable y. So there are two variables. There may be more than two variables. I am considering only two, so that's why it is called a two-dimensional random variable. X and y are defined over the same sample space, defined on the same sample space, and the results. So if we define the functions, its value will be a real number. So real number means, so if we consider x comma y as the two-dimensional random variable over the sample space S, and it will obviously a point, an x value and y value, so it will be a point on in the R2 plane or two-dimensional plane. So if xy are discrete, if we count the number of points in that plane, it will be discrete. If there are infinite number of points, or if you cannot count the number of points, it will be continuous random variable. So here we have a discrete random variable, that means it is countable in the R2 plane. Now joint probability mass function. So as we are considering x and y, there must be some mass function, but it is called the joint probability mass function. Joint probability mass function is denoted by pxy. So pxy denotes the probability of the x value equal to xi and y value at yj. So when x equal to xi and y equal to yj, what will be the probability? Is the probability of that two-dimensional random variable xy at the point xi comma yj. So it is called the probability joint probability mass function. Now it has the similar property. Always the probability is greater than equal to 0. I have not written it. But if we take the sum of all these probabilities, if we consider the sum of the probabilities at all points in that plane, in the two-dimensional plane, the sum is always 1. So this is the property of the joint probability mass function. And if we if we want to calculate the individual probability of x and y. If we consider the joint probability, if we consider the probability of a single random variable x, so it is called the marginal probability mass function. It can be obtained from the joint probability mass function by putting all y values in the joint marginal joint mass function. So here you can see the pi dot denotes the marginal probability mass function at the point mass function at xi or px at xi, and it is the sum of all probabilities where we have considered all y values. So if we run this value for, or if we get the sum of all probabilities for all j values, we'll get the marginal probability mass function for the variable x only. Similarly for y, you can get, if we put all possible values of y xi, then we'll get the marginal probability mass function for y values or y variable. Similarly, marginal distribution functions can be obtained. So here you can see marginal probability distribution can be obtained by taking the sum of probabilities for all x values up to x, but all values of y. And the for y, we have the similar approach, but here we are putting all values of x in the probability, but we are finding the sum up to the value of small y. So it will be the marginal distribution function. Now here x on y is considered to be continuous. That means there are uncountable number of points in the R2 plane. So here we can find the joint probability density function. Earlier we have defined joint probability mass function, as we are considering continuous function, continuous variable. So it will be a density function. So the definition is almost similar with the single variable concept of single random variable fxy dx dy. It is the fxy denotes the joint probability density function. Okay, and into the area dx into dy, it is the probability of the random variable in between x and at x and y. So in between, so it can be obtained by finding the probability. So you can find the limiting value so that you can get the function fxy. Similarly, if we consider if we put all possible values of x and y, or if we take the second if we get the integration over all x and y, we'll get the probability as 1. So this is the sum of all probabilities, or sum of the probabilities at all points in the R2 plane. So it is always 1. Similarly, we can get the marginal probability density function. That means it is the individual probability density function for the variables x and y. The concept is same. Here we will put all possible values of y to get the marginal probability density function of x, and if we put all possible values of x, we will get the marginal probability density function of the variable y. Now the distribution function says the sum of the probabilities up to the points x and y. So all possible values of x which are less than small x, and all possible values of y which are less than equal to y, and if we sum all the probabilities there, we'll get the distribution function. There will be equal sign in between this f of x comma y. I have done a mistake here, so please ignore part. Next is the conditional probability p of x given y can be obtained as we have done in case of events. We have here probability of happening x when y happened earlier. So it is the simultaneous occurrence of xy by probability of y equal to y. So the definition is almost same. Now next is the independence of the variable. So as we have found the marginal probability density function of x itself and y separately. So if their product is product is equal to the joint distribution, then we can say they are independent. So if probability of x equal to x, y equal to y equal to probability of x equal to x into a y equal to probability at y equal to y, they are independent. Sorry. Now, a theorem we have to remember always, as we are dealing with the multiple random variables, we have considered 2 random variables. Suppose there are n independent variables. So if xi's are independent and expected value of xi is equal to mu I and variance are sigma i's, then suppose another variable which is the sum of all these random variables. So all these variables, that means x1 plus x2 plus x2 up to xn. If we consider the sum of all these variables, that will be another variable. Suppose that is sn. So it will be a normal variate. So if we consider normal variables x1 to xn, and if we get the sum of them, and that will follow a normal distribution whose mean will be summation of mu I and the variance will be summation of sigma I. Okay, so this is an important theorem we need later. So if we consider this random variable as the sum of the variable, so they will follow normal distribution, but the condition is n must be very large or infinity. So if we consider n number or infinite number of random variables, and if we consider sum of them, then they will follow normal distribution. Okay, so in other words, we can also say if we consider n number of random variables which is sufficiently large, then their sum will follow the normal variation or normal distribution with mean summation of the means and variance summation of their individual variance. Okay, now mathematical expectations. So we can expect the value of each random variable through the formula. So here we will find the expected value of the variables. It is actually saying the mean of the random variable, and its definition, if we have a discrete random variable, mean will be expected value of x into its probability. Okay, but if it is continuous, the mean will be the integration of the product x and fx over the range of x values. Similarly, if we have a function of x for any arbitrary function, it is not necessarily that only x, we can find x square, x cube, or any linear function of x or any non-linear function of x. For all type of functions, we can find their expected value by using the formula. That function values into the probability at particular xi. It is a sum. If we get the sum of this, we will get the expected value of that function. Similarly, for continuous random variable, we will follow the same procedure, but here we will find the products of the function and its PDF. Now, some important rules we have to note here. Expected value of sum of two random variables, sum or difference, we can say difference also. So they are the sum or difference of their individual expected values. So okay, so expected value of x plus y is always equal to expected value of y. So they follow the linear property. Similarly, if x, y are independent, expected value only for the case of independent variables, it is can be written as expected value of their product is equal to the product of their individual expected values. If in expected value of any linear term ax plus b is always equals to a into expected value of x plus b. Now the variance, another important parameter. Variance, it is denoted by mu2 or var x. It is the expected value of the square of the difference x and its expected value. Sometimes it is written as x minus x bar. So xi, the square of the difference. If we get the sum of all these terms into pi, we'll get the variance of the variable. For the continuous case, we'll find the integration by finding the product of x minus x bar and fx. Now covariance. Covariance means the relationship or the variance of x and y. There are two variables, x and y, not only x or y. Both the variables are there, x and y, and covariance between them is expected value of the product of their differences, x and ex and y and ey. So we can write this like e of xy minus e of x into e of y. If we simplify the middlemost term, we'll get the last term. Now here we have to note some rules. Variance of ax plus b is always equal to a square into variance of x. You can see here b has no effect on the variance. So actually a is called the scale property or the scale of the variable, and b is called the origin. So there is no effect of origin, but there is the effect of scale. Now
সবাই এসছেন হয়তো
disturbance আসছে. Similarly, if we have sigma x square is equals to variance of x, and in that case sigma y square equal to variance of y, then we can find the covariance between these two variables, x minus x bar by sigma x, y minus y by sigma y, by using the formula covariance of xy by sigma x and sigma y. That means there is no effect of x bar and y bar, only xy and sigma x, sigma y. If xy are independent, that means their covariance is 0. There is no variation from x and y, or no effect of y on x or x on y. Now, as we are dealing with two variables, we can find the covariance. Suppose x and y denotes the set of values. So here set of values can be drawn through some points in the two-dimensional plane. So here in this diagram, we have drawn the scattered diagram of the data. Actually, these are called the bivariate data, where two variables are involved, x and y. So they have plotted in the two-dimensional plane, and we can plot them. So in this way, so you can see for each x value and y value, we have found a point in the two-dimensional plane, and in the second graph we have done the same thing. And the line, this line is called the regression line, so we'll understand later. So first of all, if we have a set of values of x and y, we can plot them in the two-dimensional plane. It is called the scatter diagram. And by checking the scatter diagram, we can identify, or we can give some insight into the data. If we have this type of data, so if we consider the first diagram, you can see at the beginning where x is very small, y values are large. But if as x increases, y is decreasing. Okay, so in the first figure we can see for higher values of x, y values are smaller, but for x, smaller values of x, y values are higher. So this type of relationship, actually here we have written r is less than 0. That means they are negatively correlated. So we'll learn correlation later, but the correlation can be understood by checking the scatter diagram. If we have such type of diagram where smaller value of x gives a higher value of y, and higher value of x values produces a smaller value of y, that means they are negatively correlated. The opposite pattern can be followed here. If we have smaller value of x where y values are smaller, and smaller values of x where y value is higher values of y, the y value is also high. In that case they are positively correlated. That means one increases, automatically another is also increasing. So that's why r is greater than 0, positively correlated. Okay, so we can understand the data by checking their scatter diagram. But suppose we have a diagram where we cannot predict, we cannot do anything with, we cannot understand anything from that data. So that means they are they may be there is no correlation may happen. Now, to understand, so if we have a bivariate data, first of all, we have to check whether the data are related or not. So data, that means there may be some relationship between the data or not. For example, if we consider the height and weight of a student. So in general, we know if height increases, weight is also increasing. So that means they are related. But if we consider the height and the marks of the student, we know height does not affect the marks of a student, so there is no relationship between data. And if we plot them in the scattered diagram, we will find they will scattered randomly. We cannot predict anything from the given data, so they are not correlated. So we may get a lower value of x where the y value is small, but in the another case for smaller value of x will gives you higher and smaller value of y. So there is no relationship, there is no relation between the variables, and they are not correlated. So this relationship can be measured through a coefficient. It is called Pearson's coefficient of correlation. Coefficient of correlation has the formula Rxy equals to covariance of x comma y by sigma x and sigma y. And correlation coefficient is always lie between -1 and 1. It is always a constant value in between -1 and 1. And if we take some transformation, if we have a large set of data with some with some large values, so we can transfer them to handle comfortably, or that means that will help you to calculate easily. So we take some transformation generator. So in that case, if we take a transformation like u equals to x minus a by b and v equals to y minus c by d, so in that case, this transformation does not affect the relationship between the variables. Okay. Now, that means transformation of the variable does not affect, if we take that type of transformation does not affect the relationship between the variables. Whatever relationship between u and v obtained will preserve in case of x and y. If u, v are positively related, x, y is also positively related, u, v is negatively related, then x, y are also negatively correlated. Now, there is a condition, p and d must be positive. If we have negative p and t, so we have to do some transformation so that p will become positive. Now, suppose we have, so here we have found the relationship between the variables. Now, next is, suppose we have two random variables which are which has some relationship. Then we can check is there any are they independent or not. Or in other words, if suppose you have given two variables x and y which are independent, but there may not be any correlation. For example, suppose here x is a normal variate and y is equal to x square. So obviously, as y is equal to x square, they are correlated. There is a relationship. Increase in x will affect increase in effect by increasing y. But if we calculate the covariance, covariance is 0. So if we have a 0 covariance, correlation coefficient is 0. That means independent variable, they are not independent, but their correlation coefficient is 0. But if they are independent, correlation coefficient is always 0. So what I want to say, if two random variables are independent, the correlation coefficient are always 0. But in case of uncorrelated data, correlated data, the correlation coefficient may be 0. Next is regression. So in case of correlation, we have understood, we have checked is there any relationship between the data or not. Now in the next case, we will study what type of relationship they have. So in that diagram, you can see we have plotted all the points, and if we draw a line through that points, so we'll get a curve, and that curve is drawn through some rule. That curve, I am not going to the rule right now, but if we are able to draw such type of line or curve, they are called the regression curves. And by checking the regression curves, we can understand the data pattern, or the relationship between the data. Now, here you can see, if we have the function of this curve, if we know the function of the curve, for any unknown value of x, we can predict the value of y. So there are different type of possibilities, or we can draw different type of curve from the given set of data. The most easiest process is the linear regression, where we assume or will state or will fit a linear curve for the data, and which has the form y equals to a plus bx. So that means here a and b are the only unknowns. If we calculate them, we can draw the line, we can get the line, and for any value of x, we can predict the value of y. The prediction or the formula of such type of curve are obtained through a theorem. It is called the least square formula. It is here we will minimize the error of this actual value and the expected value. So it is the sum of the squares of deviations of y values from the estimated value. So here y value at any xi is yi, and the estimated value is a plus bxi. So their square of their difference, and if we get the sum of them, it is the error, total error. So if we are able to minimize that total error, it will be that corresponding curve will gives you the line. Okay, so if we follow that rule, and we get two type of lines. First is the line of regression of y on x, where y can be predicted through through x, and in the second, x can be predicted by using the values of y. So we can draw them. Now here we can draw, you can check these two diagrams. The first line shows as x increases, y decreases. So here we will get values of. So if we can draw the line, or if we can write the equation of that line for any value which is not given in the table, for any value of x in between that range, we can find the value of y. So we can plot that point. That will always satisfy the equation. And these two lines, if we draw these two lines in a single diagram, they will cut at the point x bar and y bar. So obviously x bar comma y bar, that means the mean of x and y will satisfy both the equations. That means they will intersect at the point x bar comma y bar. Now, other than linear curves, we can draw several other type of curves. First is the curvilinear regression. Here we have higher order polynomials to predict or to approximate that curve. In the second is the power curve, where we can predict the curve in the form a into x to the power b equal to y, or in exponential form y equal to a b to the power x or y equal to a e to the power bx. And in the first case, curvilinear regression will follow the same procedure whatever we have done in case of linear curves. But here in the second and third, first of all we have to take logarithm on both sides to transfer this form to a linear form, and then we can follow the same procedure by using the least square method. Now, the third part of the topic is sampling theory. As we have very small, actually we have already moving late. I need 5 more minutes to explain the things. So first, sampling thing is the most important part of data science. Here actually what we do, suppose we want to study the population. Please check the diagram. Suppose this set is denote the entire population, that means the entire things, the population of a country, and we want to do or we want to study some parameter of that population. Okay, so for this we have an option to go and knock every door to check their to take the information, or we can take a very small portion of the entire thing to study and then we can predict, we can say something about the population. So, and that type of process where we take a small portion of the entire thing is called the sampling. So in general, sampling is very cost efficient, time efficient. So we generally do this frequently. There are different type of sampling. First is purposive sampling. So it will, if we want to show something, or if we want to fulfill some purpose, suppose we want to show employability of a country. So we generally take that values which will increase the employability of the persons. So generally we will take the data from the urban area or the metro cities. And the next is random sampling. Here we will take the data from the entire population randomly without giving any preference to any individual. We will take randomly the sample. Stratified sampling, so it can be done through some strata. So first of all, we can divide the entire population into different states or stratas, and then we can select small samples from each of them. Okay, and in systematic sampling, we can take data in different way, and finally we can take a simple sample. So sampling, suppose we are taking a set of n data. So it is the sample of n data, x1 to xn. So any function of that data is called a statistic. So suppose sample observations denote the height of a student. So the height of the first student, second student, or nth student. So if we measure the mean, variance, proportions, or standard deviation, all are the functions of the observations, and they are called the statistic. So here I have written the formula of two statistics. First is x bar, it is average value of all xi values, and s square, it is the sample variance, and it is 1 by n summation of xi minus x bar whole square. Now actually what we do, actually by taking samples, we generally want to know, we want to predict something about the population, and it is called the inference about the population. We want to give some insight or give some information about the population by taking a small portion of it. Okay, and always we take the sample, after taking the sample, so from the population we can take various samples, sample 1 to sample R. So there are R samples we can take, and for each sample, suppose I am considering, I am finding the means. So these values, these means are the statistics and which will follow a distribution, and it is called the distribution followed by the statistic. So obviously, as we are considering a sample from the population, as we are studying the sample only, so that means there must be some error in the calculated value, and it is called the standard error. So you have to know the standard error. It is actually the standard deviation of the distribution followed by the statistic. And if we take a very large sample from a population, as we have already discussed in central limit theorem, we have discussed, if we consider a large set of independent variable, or if we consider a set of values from the normal distribution, always the statistic will follow normal distribution. With mean is same mu, but the standard deviation will be changed, or standard variance will be changed to sigma square by n. So its square root is the standard deviation. So the statistic on basis of this distribution can be calculated by t minus expected value of t. Expected value of t means the obtained value from the sample. Is here t is the value from the population and standard error of that variable, and this statistic will follow the normal distribution with mean mu and variance 1, or the standard normal distribution. Now test of significance. So here we'll check a certain hypothetical statement. Suppose we want to check the quality of a product established by or given by some company. So what we do, we generally check their claim. So how to do this? So for this, we generally take some sample from their products, and we check or we learn study the sample. Then we'll give some information, we'll give some conclusion over the entire lot of things or entire product of that company. So for this, we'll generally do some testing. It is called the testing of hypothesis or test of significance. There are different steps to check the hypothesis. So first of all, we have to decide the null hypothesis, that means the claim given by the company or other thing. What we want to check, it is the null hypothesis. Alternative hypothesis, that means the or conjuncture to or the contrast to the given null hypothesis. The statement is whatever statement is given is called the alternative hypothesis. And this, by checking this hypothesis, alternative hypothesis, we can say, or we can consider the test, entire test, either lower tailed or upper tailed or two tailed. Sometimes it is called the left tailed, right tailed, or the both tailed. Okay, one sided or two sided test are there. So in case of lower tailed test, we can see if the value falls into if a certain value falls into the red zone, that means we can reject the null hypothesis. But if it falls into the white zone, we can accept it. But in case of two-tailed test, if we have region like this, and if the value falls into either in the left side critical region or the right side critical region, we can reject the null hypothesis. So there are different steps. Now, whenever we predict or whenever give some conclusion about the statement and null hypothesis, we may actually do some mistakes, because we are getting the sample randomly. That means the analysis may not be correct perfectly. So there are two types of errors may happen in case of statistical or inference, or we can say in hypothesis testing. There may be two types of errors. First is type 1 error. In type 1 error, what do you do? Suppose the null hypothesis is true, but still we are rejecting null hypothesis. In that case, type 1 error happens. But in case null hypothesis is false, or the alternative hypothesis is true, but still we are accepting null hypothesis. That means we are biased here. We are giving the preference to the company, whatever they say they are correct, where they are actually not correct. So the type 2 error arises there. Next is the level of significance. The probability of type 1 error is called the type 1, probability of the type 1 error is called the level of significance, and probability of type 2 error is generally denoted by beta, and 1 minus beta denotes the power of the test. Okay, so quality or the power of the test can be measured by finding the probability of type 2 errors. Now different steps are there. First of all, we will define the null and alternative hypothesis. Then we will choose the level of significance. Then we will select the test statistic, and by calculating the value of this test statistic, and if we compare that calculated value with the actual value or the theoretical value or hypothetical value of the Z variant, then we can conclude that whether the null hypothesis will be accepted or rejected. So there are different steps. 6 steps are there. I've given few examples for the first. Here we have taken the claim given by claim given as mu equal to 28, mean is 28, but then in that case alternative it is done by actually in contrast to the claim, it is mu not equal to 28, and we have taken the confidence level as 95%. 95% confidence level means we are allowing 5% error, and that much error can be written like this. This is the area of the critical region. That means 5% of entire area, or if we take this, if we consider the total area is 1, it is 0.05. It is a critical area, critical region, and that means as we are testing both the side of this mu value, that means there are 2 critical regions. That's why it is a 2-tail test. A test statistic, as we have already defined, test statistic value is 3.17. But if we check with the tabulated value or the value obtained by the density function given earlier for the standard normal variant, it will be 1.96 when the critical area is 0.025. So here the tested value of Z is, or the observed value of Z value is 3.17, but in the tabulated value, when Z is greater than 1.96, it will fall into the critical region. That means our results our test statistics falls into the critical region. That's why we'll reject H0. Now similar can be happened, but here we have considered a problem where T statistic is used because the population standard deviation was not given, so we have to use some other statistic, and this type of statistic will follow T distribution with n-1 degree of freedom. And in the third case, we have considered an example where chi-square distribution used. Actually, this is chi-square distribution generally used to test the goodness of fit, or if we want to compare 2 type of data, if we compare the quality of student in different colleges, if we want to check the quality, the marks obtained by students in different subjects. So in that 2 cases, in that type of cases, we can apply the chi-square distribution. The number of steps in the test are same, and the concept is also same. Now another thing in statistical inference is to estimation of the parameters. So we generally want to know the parameter in the population. Parameter in the population means if we want to know the average height of the population in a country, it is not possible to measure the height of every person. So that's why we'll take the sample and we'll check the height or average height of every person in that sample, and according to that sample, we'll say something about the population. So for mean, variance, standard deviation, we can predict, or we can say, or we can give some inference of the population. So it is called the estimation of the parameters. There are two type of estimations. First is point estimation, where we will get the value of the parameter exactly or approximately a particular value, and in the second case we will consider a range of values. It is called the interval estimation. We will say the parameter value will lie in between that range. Okay, so that will be run. So always we need some level of significance to state our conclusion. Okay, thank you. So if you have any question, you can ask.
Thank you, sir, for this mesmerizing session. We now take a lunch break and we will get back at 2:30 p.m. for the next part of the session. Thank you.